Today we are talking about the chapter 9 of the book, A Concise Introduction to Pure Mathematics. And in this one, we will talk about the Euler's formula. In this chapter, we'll talk about the Euler's formula and the Platonic solids. Okay, so let's do that. Now, to start with, we should know that this chapter contains a rather spectacular proof by induction. And the results we shall prove is a famous formula of Euler from the 18th century concerning the relationship between the number of corners, edges, and faces of a solid object. The result we prove in this chapter is a famous formula of Euler from 18th century concerning the relationship between the number of corners, edges, and faces of a solid object. Now, and as an application of Euler's formula, we shall study the 5 Platonic solids. So the 5 Platonic solids, which are the cube, regular tetrahedron, octahedron, icosahedron, and dodecahedron. Five Platonic solids. Now we shall call our solid objects polyhedra. So we shall call our solid object polyhedra. A polyhedra is a solid whose surface contains of a number of faces all of which are polygons. Okay, such that any side of a face lies exactly one other face. The corners of the faces are called vertices of the polyhedron. The corners of the faces are called the vertices of the polyhedron. And their sides are the edges of the polyhedron. Now, here are some examples of the polyhedron. So let's say number one, we have a cube, and the cube will be, this will be a cube. Now, this has 8 vertices. So 1, 2, 3, 4, 5, 6, 7, and 8. Yeah, 8 vertices. Then, and it has 12 edges and 6 faces. 12 edges and 6 faces. So then we have number 2, we have tetrahedron. And for tetrahedron, we have it's kind of a similar fig, similar to the tetrahedron, but like there are few lines regular. And then this has 4 vertices. 1, 2, 3, 4. 6 edges. and 4 faces. Then we can write the number 3, which is triangular prism okay, and this one will be the triangular prism. This is triangular prism, and this has this has 6 vertices, 9 edges, and 5 faces. So you can write the say we have 1, 2, 3, 4, not 4, 3, 4, 5, and you can say 6 here. Okay. Now, yeah, number 4 we have is n prism. And n prism is like, this is like a triangular prism, except that its top and bottom faces are n-sided polygons rather than triangles. So this is like triangular prism, except that its top and bottom faces are n-sided polygons rather than triangles. It has two n vertices, 3 n edges, and n plus 2 faces. Okay. Let us now collect the number of vertices, edges, and faces for the above examples in the table. Does these numbers V, E, F respectively denote? So let's say we denote vertices with V, edges with E, and faces with F. Then we can write these in a table that will be V, E, F, So 1, 2, 3, 4. That will be 8, 12, 16, and the cube 4, 6, 4, 6, 9, 5, 2n, 3n, and plus 2. Can you see the relationship between these numbers that holds in every case? So the relationship between these numbers that can hold in every case is vertices minus edges plus faces is always 2. This is Euler's formula. And we shall show that it holds in general for all convex polyhedron. We show that this holds for all convex polyhedron. Now, a convex polyhedron or a polyhedron is convex if whenever we choose 2 points on its surface, whenever we choose 2 points on its surface, the straight line joining them lies entirely within the polyhedron. Okay. So all of the above examples are convex polyhedron. However, if we, for example, take a cube and remove the smaller cube from its interior, we get a polyhedron that is not convex. For this polyhedron, in fact, V has vertices 16, 24 edges, and 12 faces. And then, so V minus E plus F is 4. The formula fails. Here, then, okay. So in the next part, we will explain the Euler's formula. In this one, we have explained the Platonic solids, and then some of them. We have mentioned that. See you in the next part.